Hey there. So welcome to our video on sinusoidal functions. I'm pretty excited about this one because we're actually going to get to use trig functions to model stuff in the next couple of classes, and sinusoidal functions are how we do that. So what is a sinusoidal function? Well, it's really just a sine function or a cosine function that's been through one or more graph transformations. That's it. So to understand this video, we kind of just have to have a basic sense for what sine and cosine look like, and it'd be good to refresh what you know, or even have Desmos open while you're working on some of these problems. And also to remember how graph transformations work too, which is something we've talked about at the beginning of the year. So what can we model with sinusoidal functions? Well, waves are a big important example. And we use these functions for everything from ocean waves to sound waves to electromagnetic waves. Waves are everywhere. But also just any system that oscillates back and forth. So something like a spring in physics to things like temperatures throughout the course of the day or even the course of the year. So sinusoidal functions have basic properties we're going to want to know about, and they come from these graph transformations that we're doing to them. All right, let's get started. So amplitude is the first property that I want to talk about. Amplitude is basically just a measure of how much the graph has been stretched vertically. So strictly speaking, it is the distance from the midline of the graph. And I'll use this as our first example. The midline is usually y equals 0, unless some shift has happened to the graph. It's the distance from there up to one of the peaks. Okay, so for example, for this function on the left, it would be the distance from 0, y equals 0, up to y equals 3, which is where this peak is. So I would say that that amplitude is 3. Which also happens to be how much I've stretched the sine graph by. This is y equals 3 sine x, so that's not really much of a surprise. So in terms of how this gets used, I mean, amplitude of a sound wave, for example, is volume. So it can be a measure of something like how much energy the wave is carrying, although that's not always the case. So it's pretty easy to adjust and also detect. Like, for example, this is y equals 1/2 cosine x. I've multiplied it by 1/2, so I've changed the amplitude from 1 to 1/2, and we can see that the distance from here up to the top is 1/2. This graph, I'm not going to tell you what the formula is. If we want a way to compute the amplitude for something like this, one kind of easy trick for doing it is take the distance from the bottom to the very top. So that's -2 all the way up to 6. That's a distance of 8. And then just cut it in half, right? 8 divided by 2 is 4. Okay. So amplitude's pretty easy. Wavelength and frequency are a little bit more complicated, but not too much really. So the wavelength of one of these functions is a horizontal distance. It's the horizontal length of one peak and one valley, right? Which, if you put those together, is a complete cycle of the graph, where the graph has gone both up and down and then returned back to the middle. So we call that full length a cycle, and the length of a cycle is the wavelength. Okay, so for a standard y equals sine x, unsurprisingly, that's 2 pi, right? 2 pi is how long it takes to go up and then down and then back to where you started. So wavelength we've kind of already seen before. It's also the same thing as the period of one of these graphs, right? And that's because the function is going to repeat after every cycle. It's periodic. So the period of a sinusoidal function is equal to the wavelength. Sometimes wavelength gets called lambda. I'm not going to stress too much about particular variables in this class, but you might see it in other classes. That's what this Greek symbol down here is. It's a lambda. Because the wavelength is the same thing as the period, it's a truth that if I add lambda to x, I get the same thing back as the original function, right? That's the property of periodic graphs that we've seen before. Okay, so how do we change the wavelength? Well, we just like stretch the graph or shrink it horizontally, right? And we have to remember that when we're talking about horizontal graph transformations, they always work backwards, right? So if I multiply x by a number like 2, for example, that's actually going to cut the wavelength in half. It's going to have that opposite effect because I'm going to be shrinking the graph. And let's see some examples. So y equals sine of 2 pi x. Well, the wavelength started at 2 pi, but because I've multiplied x in the function by 2 pi, that has my new wavelength is 2 pi divided by 2 pi, which is just 1. So quite often you see that like people starting not with sine of x, but with something like sine of 2 pi x, because that just normalizes the wavelength to be 1 to start with. Something like y equals cosine of x over 2. Well, okay, cosine also starts with a wavelength of 2 pi, but when I divide x by 2, that multiplies the wavelength by 2, so that I end up with 4 pi, right? So these wouldn't be things that, like, this isn't something that I could just measure by hand because I can't spot 4 pi, but if I have my formula, I can tell exactly what it is. So wavelength is very closely related to frequency. Frequency is the number of cycles per unit length. Okay. So it has to do with like how many cycles fit in one length this way. And it's not hard to think about it. It's like the longer the wavelength gets, the smaller the frequency is going to get, because if you have longer wavelengths, you're not going to be able to fit as many of them in the same distance. So they have this inverse relationship. And in fact, the frequency is always equal to 1 divided by the wavelength, or 1 over the wavelength. So how do these things get used? Well, in a pretty big way, actually. Like frequency, or wavelength, however you prefer to measure it, is going to affect the pitch of a sound wave. So like whether it's a really high note or a low note. And when we're talking about electromagnetic waves like light, for example, it affects like the color of light, or the amount of energy of the electromagnetic wave, whether we're talking about like radio waves or infrared waves, or like gamma waves coming from a nuclear blast. Like all of those are defined by what the frequency actually is. So it plays a huge, huge role in science. Okay, there are formulas for computing these things, unsurprisingly. And I think it's good to use your intuition a lot instead of these formulas. But I'll tell you what they are. So for example, the function like sine of cx, if I'm multiplying x by c, then the wavelength is equal to 2 pi divided by c. And the frequency, remember, is just the reciprocal of that. So it's going to be c divided by 2 pi. Really not too hard to explain where these formulas come from. I'll let you work them out. I don't keep them in my mind a lot, because when I'm doing these things, I'll look at whatever the graph transformation happens to be, and then work it out from what I know about graph transformations. But you're welcome to remember these formulas if you like. Okay. So the last thing to talk about, not a huge thing, are shifts in the graph. Not too much to say here. If we take a sinusoidal function and we shift it left and right, so a horizontal shift, that's often called a phase shift in the graph. Doesn't affect too much scientifically. But if you're trying to model something, you want to make sure that the intercepts are in the right place. If we're trying to model the temperatures throughout the year, we want to make sure that the lowest temperature happens in winter and the highest temperature happens in summer. So we might have to shift the graph left and right to account for that, right? So if you remember your graph transformations, you're not going to have too much trouble here. For example, like cosine of x minus 1, well, it's a horizontal shift, and that means it's backwards, right? So I'm actually moving the graph of cosine to the right by 1. And that's why the peak in the graph happens over here at x equals 1 instead of over here where it would normally happen. Okay, vertical shifts, not super common with these types of functions, especially not when we're talking about sound waves or electromagnetic waves. But we say that they like change the midline of the graph, which I've mentioned before. That's just the horizontal line that goes right through the middle of the graph, right between the highest and lowest points. So normally that's y equals 0, but if you add 3 to a function, for example, then it's going to push it up to y equals 3. So here's just a very simple example of that happening, right? Sine of x plus 2. The plus 2 is not in parentheses, so it's something that I'm doing to the entire function. I want to be careful about parentheses right now. So it's going to push the midline up to y equals 2 and the rest of the function with it. Okay, so here's the homework. I would like you to try to find, I'm giving you the graphs, I'm giving you what the sinusoidal function looks like. I want you to find the formula for that function. And think about it as what series of graph transformations have I done to either sine or cosine. Okay, and if you're wondering like which one do you start with, well, sometimes there's a natural choice, sometimes there's not, and you're welcome to start with either one. So that can result in more than one answer that is correct to a problem like this. I will walk you through the first one and then try the other two on your own. Okay, so here's, for this function, I'm gonna start by like seeing, well, what's the amplitude? That's a good place to start. Well, I can see that the distance from the middle up to the top is 5. Okay, so that means that I've taken one of these functions and I've multiplied by 5. Which function should I start with, sine or cosine? Well, the fact that the peak is right along on the y-axis, like with cosine, means that probably cosine will be a little bit easier. But sine would work too. I would just have to do some horizontal shift to make it work. So I'm going to start with cosine, and I'm going to start by multiplying by 5, because that's going to change the amplitude to be the right thing. Now I need to think about the wavelength, or the frequency. Usually wavelength is an easier thing to work with first. So what can I tell about the wavelength? Well, it's the length of one peak and one valley. So that I could start at -2, go through one peak, one valley, and then end up at 6. So that horizontal distance is 8, not too hard to see. So that means that I want to make the wavelength equal to 8. Okay, and here's how I do that in my mind. The wavelength of cosine right now it starts at 2 pi. So first I will make it equal to 1 by multiplying x by 2 pi. And now I need to go from 1 to 8. So I should, remembering that it's opposite, I should divide this by 8. Let's see if that does it. Good. Okay, so, and I could do some simplification there. I noticed that like 2, I could cancel a 2 from the top and bottom, so I would end up with pi x over 4. That's not super crucial. I wouldn't worry about that too much, but I can make it look a little nicer. And that's should already be enough. So I've stretched it vertically to get it up to 5, and I've stretched it horizontally to make the wavelength the right thing. I don't need to do any shifting up or down or to the left or right because I started with cosine. So that should be good. And you can check in Desmos that I've gotten the right thing, right? That it has all the right intercepts. And that would be a great way. I encourage you to check your answers because it's good practice in using Desmos with this stuff anyway. So why don't you give that a shot with the next two? And I won't post the answers because I'd like you to check those on your own. And we'll talk about it in class. All right, see you then.